Hi, I'm Lane Fuller,
I'm Patrick Scheffer.
and we're going to introduce you to our project, which is MPC controller for BB-8.
We are first going to start with the 1D model we created to describe the dynamic motion in one dimension.
And then we'll move on to the 2D model that we created and watch some simulations of the robot moving around. Let's get started.
In order to do MPC control, we need a model for the system. So our system is the spherical robot BB-8 from Star Wars, which was built by Lane and his classmates for a different class project. So it consists of a sphere which contains a robot, and this robot can drive with 4 omni-wheels in every direction inside the sphere. So you can see our one-dimensional model on the screen now. We simplified the system, so now there are 2 contact points on the sphere and the body inside. The state variables of the system will be the angle of the body, theta b, and the position of the sphere, xs. To find the system dynamics, we just sum the forces in x and z direction and the moments in the mass centers about the y-axis. So this figure here shows the forces acting on the spherical shell of the body. So we have these normal forces between the sphere and the ground and between the sphere and the robot on the 2 contact points. The input force is shown in the middle of the robot. We chose to have it act at this location since it is more representing of the real system. We assume rolling without slipping everywhere, so the friction force Fs between the sphere and the ground is our last unknown here. Now this last figure shows the subsystem of the robot inside of the sphere. Now everything is turned the opposite way, it's nothing new, but we can see the same forces acting in the opposite direction.
Now that we have the 1D model of the robot, we can simulate the motion in MATLAB. And we use this output to create a 3D animation. This first video you see is the reaction to a predefined set of inputs. First we apply a torque for a period of time and then let the robot coast. Then we apply a torque in the opposite direction to have the robot brake and stop. Next we apply our MPC control to the robot. In this video we apply a reference point of 1 meter and let the robot react. Here we do the same thing, but give a reference point of 10 meters. In order to control the robot's 2-dimensional motion, we have to modify our model a little bit to account for this extra degree of freedom. This first picture you see here is the top view of the robot in the sphere. We modeled the robot with 3 wheels and 3 input torques shown here. Having these 3 input torques and 2 outputs, x and y, makes this model a MIMO system, unlike before. To generalize to 3 directions, we need 2 components of the friction force shown here, Fx and Fy. Next we move to side view to show that we now have 3 normal forces on the wheels instead of 2. The normal force on the sphere is not shown because that does not affect the output of the system. The process for getting the equations of motion are the same as before, but more complicated because we are working in 3 dimensions. This time we use the vector form of Newton's second law and use rotation matrices to express the angular position of the robot inside the sphere.
Similar to the 1D case, here are the renderings of some 2D MPC control simulations from MATLAB. The reference trajectory is a square with side length 5 meters in the simulation. We provided steps in the reference here, so the MPC controller wants to move the system to the corners as fast as possible. And then it stops there until it receives a new reference. Also the future reference trajectory is not known to the controller here. We see in this example that we have some basic problems when we are controlling the system. When going in the x direction, we see that the robot stops in halfway and then it moves back and forth once. When going in the y direction, the robot moves in the wrong direction first. These problems might indicate some errors in our 2D model or the parameters we chose. This rendering also shows the sphere moving in a square. But this time the reference trajectory is not given stepwise, but like a ramp. So we increase the value for the designed position continuously. Also, the future trajectory is known to the MPC controller this time. We noticed that the movement is a lot smoother now. We don't have this back and forth motion anymore. It seems that the radical changes in speed or direction might cause the robot to behave erratically.
Here we give the robot a circular trajectory to follow. Much like the previous examples, the MPC controller behaves strangely and produces inputs that don't appear to be optimal. But when the robot is moving at a constant speed, it follows the trajectory quite well. Because we did not include theta z of the sphere as one of our states, we did not define it in the animation. This is why the rotation of the sphere looks strange.
So this wraps up our project. The next steps would be to improve our model on one hand. The point to improve would be the moments of inertia. At the moment we're using the same moment of inertia for rotations about all three axes. And we could imagine, for example, the z-axis especially, it should be quite different from the other two. So we could even imagine making them dependent on the current angle of the robot. And the second point would be to add some kind of mechanical loss into the system, maybe some friction, to also make the system more stable if you don't apply any control inputs.
Yeah, and the last step would be to implement this controller on the real robot. In order to do this, we would first need to relate the motor torques to a voltage that we would apply, because that would be the real input. And finally, we would need the controller to work in real time so that we would be able to control the robot successfully. Thank you.